So now we are ready to do some practice on kinetic molecular theory, gas laws, and ideal gases, and we're going to put it all together. All right, so let's look at what we've done so far. At this point, you've learned about kinetic molecular theory, you've learned about the basic gas laws, you've also learned about ideal gases and the units that they must use. For example, we must do all of these gas law things in Kelvin. If you want to convert to Kelvin, it's just Celsius plus 273.15. You've taken a look at SI units. You've done questions 1 through 10, shown your work here. You've done some unit conversions. You've taken a look and you've done questions 1 through 6. All right, homework will be to do questions 1 through 14 down here. You've also taken a look at the metric system. These are also unit conversions. So 1 meter, kilometer would mean 1,000 meters. Millimeter would mean 1,000th of a meter. So we have 1,000 millimeters in a meter and 1,000 meters in a kilometer. All right, and you've done questions 1 through 15. These are your homework in here to help get you comfortable with this specific type of unit conversion. Got answers at the bottom if you need help. You've done all that. Now it's time to put it all together and just start doing some practice. So this starts out with a cause and effect table. So I actually made an error here though. Sealed container means that no amount of gas can get in or out. So actually this should have said rigid container. Sorry about that. Rigid means the volume can't change. So let's think about this a little bit. Our ideal gas law is PV equals nRT. So the amount of gas in a rigid container decreases. Okay, so we know that this is the thing that's changing, the amount of gas. Okay, so I'm going to put a little dot there. That is changing. The assumptions, the volume and temperature of the container stay the same. Okay, the volume and the temperature stay the same, so these two are not changing. And the constant never changes because it's a constant. That means the pressure must be the thing that's changing. So don't look at the effect yet. Let's think about this. If the amount of gas in the container decreases, so this side of the equation decreases. We know volume's not changing, so what's going to happen to pressure to keep this equal on both sides? Well, if this side decreased, then pressure must also decrease. So that would be our effect. The pressure in the container will decrease. So you're going to fill in effects, and then down here, you're going to figure out what the cause was. And then you've got some questions that are connect this to engines. And then you've got some gas law problems down here. I thought we would do one of these together so you can see what it looks like to apply the ideal gas law. So let's do number 5 together. Okay. So once again, I always like to start out my problems by writing what I think I'm going to use. Okay. If a gas has a pressure of 84 kilopascals and a temperature of 35 degrees C, and it is heated an additional 230 degrees C, what will the new pressure be? Assume the volume of the container is constant. All right, so if the volume of the container is constant, it's not getting larger or smaller. I also didn't hear anything about the amount of gas changing. So we know volume's not changing, and I didn't hear anything here about the gas changing. Sealed container, we're going to assume that. Okay, well, it looks like all we've got here is pressure and temperature. Well, that's good news, so that's going to make our life fairly simple. That means that what we're going to use is one of the gas laws instead of the ideal gas law. So let's go back to that page and see what gas law we think we're going to use. We got pressure and temperature. That's going to be Guy-Lussac's law right here. All right, so going back. All right, the constant never changes, so we're going to say pressure 1 over temperature 1 is going to be equal to pressure 2 over temperature 2. Now, there are a couple tricky things in this problem. It's in Celsius, so we need to convert to Kelvin. And take a look at this word here, additional. Additional means it's going to be 35 plus 230 is going to be our second temperature. It gave us the first pressure, so you're going to be solving for the new pressure. All right, so that's how you set up that problem. Let's take a look at number 5. If 4 units of a gas, all right, units, this is, we've talked about this a little bit, mole. You don't really know what that means yet, but you can think of it as we've counted up the amount of gas. So if 4 moles of a gas at a pressure of 54 atmospheres have a volume of 120 liters, what is the temperature of the gas? Ooh, there's a lot going on there. Let's figure out what's going on. So once again, I always like to start out my problems by writing PV equals nRT. All right. And in the previous problem, we crossed out things that weren't changing, and it helped us identify which gas law to use. Let's see what's going on here, though. 4 units of a gas. All right, that means they've given us an N. We've got a pressure of 5.4 atmospheres. All right, so that's our P. A volume of 120 liters. That's our volume. It wants to know the temperature. Okay, this is doable. It's given us pressure. It's given us volume. It's given us moles. The constant we can choose from the pressure. That means we only have one unknown. We're going to be solving for temperature. All right, so let's set this problem up. Scoot this down a little bit so I can zoom in. All right, let's set this up. So P is pressure. That's going to be 5.4 atm. That's the P. So P times V. So we're going to do this times volume. Where's the volume? Here it is, 120 liters. Good. That's going to be equal to the number of moles. They already gave us that. 4.0 moles times R. All right, what should our R value be? The R value depends on the pressure, and the pressure here was given in atmospheres. So let's flip back to our ideal gas law page and figure out what R constant. If we're using atmospheres, we should be using 0.082. So here we go, 0.082, and the units on that are ATMs. Well, what were the units on that? They're all going to cancel out, so it doesn't matter a ton, but I like to keep track of my units. Liters times atmospheres over moles times Kelvin. Atmospheres times liters over moles times Kelvin. Okay. And we're solving for X. We do not know the temperature. All right, so grab your calculators, figure this out, pause this video, and then you can press play and see how I did the math on this. All right, so I got my calculator here. First thing to do, we can multiply some of these together to make this simpler. So 5.4 times 120. Okay, that's going to be 648 atmospheres times liters. And that's going to be equal to the other side. Now we're doing moles times something with moles on the bottom, so moles are automatically going to cancel out here. And remember that the temperature is going to be in Kelvin, so we've got a unit over here. So 4.0 times 0.082. Okay, we've got 0.328, and that's going to be atmospheres times liters over degrees Kelvin. All right, so, and all of this, remember, is still times X. So how do we get by X by itself? Well, we're going to divide this side by this side. Now, automatically, if we divide atmospheres times liters by atmospheres times liters, we know the units are going to cancel out. We're going to be left with Kelvin. That's great. Can we do 648 divided by 0.328? Yes, what do we get there? So this divided by 0.328 ATMs times liters over Kelvin. Okay, wow, we've got an answer there. Right, so it looks like X by itself is going to equal 1,975. Now, how do we round? Well, let's take a look. We've got one decimal place here, none there, one there. Yeah, I'm going to stick with one decimal place. There are ways to figure out exactly what this should be, but today's not the day. All right, so there's my final answer. I'm going to circle it. I've got my units on there. 1,975.6 degrees Kelvin. And you see at the bottom, it says 1,974. Did we make a mistake? Probably not. It was probably a rounding thing. I wouldn't worry too much about it. If your answer is very close, you're not going to lose points on this. So that is how we use the ideal gas law to solve a problem like this. So I'd like you to continue doing some of these problems, but if you want some practice before you work on the stuff that I will eventually grade, good news, I have some practice for you. So let's make this small again. Questions 11, 12, 13, 14, and 15 are a little bit more and 16 are a little bit more complicated. So these will give you some practice on unit conversions, things like that. For example, I started number 11 over here. This is what page 72 is for. Page 72 is for you to do some of these practice problems if you want some space to work on those. Let's see, I read this problem. It says at 1,200 torr pressure, we've got a sample, 400 milliliters of nitrogen, and the temperature is 250 K. All right. They didn't tell us moles of gas, and if this container is sealed and inflexible, that means that the volume of the container is not going to change. So anytime you see sealed and inflexible, okay, inflexible or rigid is a way of telling you that the volume isn't going to change. And anytime you see sealed, that's a way of telling you that the amount of gas is not going to change. So we don't have to worry about volume. We don't have to worry about amount of gas. We don't have to worry about R because that never changes. It's a constant. So it turns out this is a pressure and temperature problem. Well, pressure and temperature problems, let's think. What gas law is that? Whoops. Pressure and temperature, that's going to be Guy-Lussac's law again. All right, so let's take a look back here. It says the container will rupture at a pressure of 1,800 torr. So we don't even have to do unit conversions on this one because we've only got 2 units that we're working with. So we're gonna have pressure 1 over temperature 1. It's gonna be equal to pressure 2 over temperature 2. All right, our first pressure is 1,200 torr, and our first temperature is 250 Kelvin. And the question asks, what temperature will it rupture at if we know that the pressure will break the container at 1,800 torr? So that's going to be your second pressure, and you're going to be solving for your second temperature. The reason you need to know ideal gas law for this is you need to know what things you can ignore, and it helps you figure out which gas law to use. It's possible you will also run into some gas law problems where you actually need to use the full PV equals nRT like we just did over here on question number 5. Let's see. Now, if you'd like some practice on those, you can scan this QR code right here. And this QR code will take you to a pretty cool page. It takes you to this. This is the gas laws quiz page. Over here, you can set anything you want for your practice problems, okay? If you want to only work in ideal gas law problems, you can just click ideal gas law and it will give you exactly what you need. You can also decide what units you see. You can decide whether or not it's a word problem. You can say how you want it. Do you want it just on the screen for you to click? Do you want it to print you out a worksheet, etc.? And you press start and it'll make you some problems to work on. All right, so those are some ways you can practice this. All right. But when you're ready, I'd like you to finish this page. These are the ones that Ms. Schrock and I will actually be grading to see how you apply scientific language, meaning can you show comprehensible mathematics, and how you use science to address the problems. All right, folks, so that's what you're doing today. You got plenty of opportunities to practice this. You got these practice problems, these practice problems, and you've got some homework to do too. So there you go, my dears. Onward.